Greetings to all. This is Mrs. Nitya Sanghvi, Assistant Professor, Civil Engineering Department, IPS Academy, Institute of Engineering and Science. This is a lecture on rolling loads and influence lines, part of the curriculum Structural Analysis 1 CE 403. Let us define what is a load. A load is a force tending to effect and produce deformations, stresses, or displacements in the structure. We can also say that a load is any external agency encountered by a structure that tries to deform or deflect the structure. Generally, there are two types of loads that are encountered by the beam: dead and live. Dead loads are those loads which do not change their positions during the life of the beam. Example: self weight of the beam, weight of the slab carried by the beam, finishing load, etc. Now, what are live loads? These are the loads which change their positions during the life of the beams. Example: weight of the person on the slab or beam, weight of furnitures, etc. Now we come on to the main topic, rolling loads. Rolling loads are the loads which roll or move over the given structural element from one end to the another. As we all know that a designer has to analyze the beams for various positions of loads so as to get maximum shear force and bending moment values due to moving loads. For this purpose, they need what we call as influence line diagrams. These are abbreviated as ILD. So, ILDs are drawn for various stress resultants like reaction, shear force, bending moment, torsion, etc. ILD for a stress resultant is the one in which ordinate represent the value of the stress resultant for the position of unit load at the corresponding abscissa. The following videos will show the ILDs for simply supported beams, cantilever beams, overhanging beams, double overhanging beams, and concept has been introduced to plot the ILDs for three hinged arches. So now we are starting with the ILDs for simply supported beams. We are having a simply supported beam hinged at end A and roller at end B, having the span of L. And we have been given a section C, which is Z distance from end A. Now we have to plot the ILDs for RA, that is reaction at A, RB, that is reaction at B, shear force at section C, and bending moment at section C. First of all, we'll see the sign convention. This is the beam and this is the section. Whenever a load in the right portion acts upwards, we get a shear force which is negative, and we get a bending moment that is positive. Now, whenever a force in the left portion is acting upwards, we get shear force as positive and bending moment as also positive, because this bending moment is trying to sag the beam, and sagging bending moment is considered as positive. Also, in our convention for ILDs, up means positive and down means negative. And also we have to provide rotation in the clockwise direction, and it will be considered as positive again. For plotting the ILD for RA, we will draw the beam once again. Now let us consider this matchstick as a beam AB. For plotting the ILD for RA, simply hold the end B, lift the end A with an ordinate of unit dimension. Right? This is the given ILD for RA. Unit. Right? For plotting the ILD for RB, Simply hold the end A and lift the end B with an ordinate of unit dimension. And we will get the ILD for RB. Now for plotting the shear force at the section C. What we are basically doing is that we are tearing apart the beam at the point C. Now, as we have seen the sign convention, RB is acting in the upward direction in the right portion of section C. So we have to negate the ILD for RB for plotting the shear force. Now for RA, the figure will be drawn as it is, and for RB, we will negate the figure. Now, as the section is getting teared from point C and A and B are in their own position. So, this is our resultant shear force ILD. And the ordinate is Z by L, and here the ordinate is L minus Z by L. Now, for plotting the bending moment at section C, we will provide a clockwise rotation, right, at point C. After providing clockwise rotation, we will get some sort of bending, like from the point C we are bending the beam. The beam is going downward, right? But what figure we will get? We will get a triangle. Actually, basically C point is there. We are bending like this. Suppose it is getting braked, and this is the rotation provided at point C. So, the bending moment will be positive triangle as we have got over here, right? And the ordinate will be Z into L minus Z by L. This is positive. Here this part is negative and this part is positive. So these are the ILDs for simply supported beam. I think I am making myself very clear to you all. Now we have to plot the ILD for cantilever. We are having a cantilever beam that is fixed at end A and free at end B, having a span L, and we have been given a section C which is distant Z from end B. For plotting the ILDs for RA, bending moment at end A, shear force at the section C, and bending moment at the section C. We are having the beam AB. This is our beam AB, right? And A is fixed. What do we mean that the end is A is fixed is that no vertical movement, no horizontal movement, and no rotation allowed. So when we are lifting the end A with an ordinate of unit dimension, for plotting the ILD, the whole beam will lift up because end B is already free. There is no support. So we will get the ILD for RA as such, a triangle in the positive direction with unit dimension ordinate. For plotting the bending moment diagram ILD at end A, we will provide clockwise rotation to end A. This will be our ILD for bending moment at A in the negative direction, having dimension of L, right, because we are considering load as unit load. For plotting the shear force at section C, basically we are tearing the section at C. The section is tearing the beam at the point C. Like simply we are providing a cut over here. After providing the cut, as the end B is again free, we will provide a unit ordinate and simply it will get lifted up from the point C, and the point at A will remain as it is. So only this part will lift up, CB, right? For plotting the bending moment at the point C, what we will do, we will provide a rotation at C. AC will not move, only CB will move in the again negative direction, because we are providing a clockwise rotation, negative, right, with ordinate of Z. So these are the ILDs for cantilever, right? I think I am making myself very clear. Now we will plot the ILD for overhanging beam. We are having an overhanging beam having end A hinged, B roller supported and free end C. That is, the BC portion is overhang. The span of AB is L. We are having a section D at distance Z from end A. We are having the dimension of BC as A, and we are also having another section E distant Z1 from end C. Now for plotting the ILDs, first we have the stress resultant RA. For plotting the ILD for RA, first of all we will lift the end A with the ordinate of unit dimension. As support B is there, so it will go like this, and since BC portion is free, it will go downward, having a dimension of A by L. This will be positive and this will be negative. Now we will plot the ILD for RB. We will lift the end B with unit dimension like this. The beam will get lifted and it will go straight upwards, as again the portion BC is free. We will have this height as A plus L by L. Now we will plot the shear force at section D. We are having this beam, this is B, this is D. Now if we consider AB as a simply supported beam, we have earlier drawn the shear force for the section as this, and since BC portion is again free, it will go downwards like this. Now the dimensions for this will be Z by L, L minus Z by L, and this will be A by L, right? Now we have to plot ILDs for bending moment at D. This is our beam, this is point B, A, and this is D. As we have drawn earlier, we will consider AB as a simply supported beam. This will be our bending moment diagram, and this will again go downwards till C, because again BC portion is free. This dimension will be Z into L minus Z by L, and this height will be AZ by L. Okay. Now we have to draw ILD for shear force at section E. This is our beam, this is portion B, this is point E. Now as BC portion is free again, so A to E, it will behave as a cantilever, and as we will provide shear at E part, so it will be basically what will happen, it will go upwards with unit dimension. This will be our shear force for E, right, as we have seen in the cantilever part. Now we have to draw bending moment at section E. This is B and this is point E. As we have seen in the cantilever, again A to E part will behave as a cantilever, and when we are providing bending moment, it will be negative and of dimension Z1, right? Now we will draw the ILD for double overhang beam. That is having two overhangs, right? This is portion D. This is our first support A, that is hinged. This is portion B, that is roller, right? And this overhang is E. We are having a section C. Span of AB is L and this portion is Z. DA is small a and BE is small b. Now we have to draw ILD for the stress resultant RA, which will be, we will lift simply end A with an ordinate of unit dimension, same as we have done in the simply supported beam case. This will come downwards because B part is free, and this will go upwards as AD part is also free. This dimension is 1, it is in the positive direction and this is in the negative direction. This portion will be B by L and this ordinate will be L plus A by L. Now we will plot the ILD for RB. Simply we will lift the end B like this with unit dimension and it will go straight upwards as BE part is straight, as we have seen in the single overhang case. This portion, the height will be L plus B by L and this portion will go downwards and the height will be A by L and it will be negative. Now we have to plot the shear force, right, at section C and bending moment at section C. This is our beam. We have to plot the shear force at section C. Now here this is A and this is B and this is C part. Now as we have seen in the simply supported case, the portion will be like this for simply shear force if we are considering AB as a simply supported beam. This portion will go downwards as BE portion is straight and this part will go upwards as AD portion is free. So the dimensions for this, the height is Z by L as we know and it is negative. The height here is L minus Z by L and positive. This portion, this height will be, it will be negative and the height will be B by L. Over here this portion will be positive and height will be A by L. Now we are supposed to find out the ILD for bending moment at section C. This is the point. Again we will consider AB as a simply supported beam. We are having the same figure as we have plotted for simply supported beam, a triangle positive. Since BE part is free, it will go downwards like this and here also it will go downwards like this. The dimension over here is Z into L minus Z by L. This part will be negative, having a dimension BZ by L. Over here this portion will be negative with a dimension of A into L minus Z by L, right? Now our numerical problem is being given. It is known as a balanced cantilever having end A hinged, B roller, E roller and F roller. G is a section provided. C and D are internal hinges. Now we have been asked to plot the ILD for RA. Simply we will lift the end A with unit dimension. Now as internal hinges are provided, it means movement won't be transferred further. So like ABC remains one portion, CD another and DEF one portion. It will always be straight until and unless a shear is provided in between them. So for plotting the ILD for RA, we will lift the end A with the ordinate of unit dimension. It will go down to B. From B it will go down straight to C and it will get connected again to D. As this is unit dimension 1, right? So this will be 0.25. It will be negative, it will be positive. Movement won't be transferred further from point D. This is point C, this is point D. Now we have been asked to plot the ILD for RB. We will simply lift the end B with ordinate of unit dimension. It will go straight till point C, as A, B, C have to be straight, and it will go down to D point, right? This triangle will be there. This will be the ordinate, and the ordinate at the point C will be 1.25. This will all be in the positive sense. Now in the same question we have been asked to find out ILDs for shear force at C. C is basically what? Internal hinge. Now this is the point B, this is C, this is D, and this is E, and this is F. This is A. For providing shear at C, simply it will go upwards, this portion with unit dimension, because C, D are free from whole beam, but it will come down to point D because D is not getting lifted up. Only shear is provided at point C, and this will be positive. For plotting the shear force at G, that is the section in between A and B, right? This is B, this is C, and this is D. This is point G. What we will do? We will consider AB as again simply supported beam. So this portion will come downwards, this portion will go upwards, and it will get connected to B. As A, B, C have to be in the straight line, so this portion will go down till C and it will get connected to D, right? This dimension will be 0.5, this will be 0.5, and this dimension will be 0.25. This will be negative, this positive, and this whole portion will be negative. Now we have been asked to find out the ILDs for bending moment at point G. That is the section in between AB. This is A, this is G, this is B, this is C, this is D, this is E, and this is F. Now for providing bending moment at G, we will again consider AB as a simply supported beam in which this portion will be a triangle upwards, go down to B. As A, B, C have to be in the straight line, it will go down till C. Again it will go up towards D and stop because movement won't be transferred beyond point D. The dimension will be 5 5s are 25 upon 10. So this height will be 2.5, and so this height will be, what will this height be? It will be 1.25. This will be negative and this will be positive. For finding out the bending moment at B, this is B point again. We will provide clockwise rotation at point B. This will go down to C, right, and again it will come upwards to D. This will be the ILD for bending moment at D, and this dimension will be nothing but 2.5 in the negative, right. So these are the ILDs that were asked to be plotted for the question, which is known as balanced cantilever, right. Also come across the cases when rolling loads are there basically. So this is a rolling load of 40 kilonewton per meter and having a span of 5 meter. It will roll over the beam and we have to find out the shear force at section C and bending moment at section C. So first we will draw the ILD for shear force at section C. As we have drawn for simply supported beam, it is very easy. Same figure will be there. This dimension will be 6 upon 15. This dimension will be 9 upon 15. Right? This is negative and this is positive. Now we have to find out the shear force at particular section. Okay. So first of all, we will find out the negative shear force. Negative shear force means the UDL should be in this part. For UDL to be in this part, since this is 6 meter and UDL is of span 5 meter, and to get the maximum value for negative shear force, the head of UDL should touch the section. This will be 5 meters. Right? This whole portion will be covered. So we have to find out this ordinate. This ordinate would be, now as the distance from A to C is 6, so we get the ordinate as 6 by 15. So when the dimension is 1, we will get the ordinate as 1 by 15. So to find out the negative shear force, we have to find out the area under the load. That is trapezium area half into sum of parallel sides, that is 1 upon 15 plus 6 upon 15, right, multiplied by the base is 5 into the UDL, which is 40. This will give us the negative shear force. Now we have to find out the positive shear force. For this, we will assume that UDL travelled and its tail is at now C and its head is after C. So the dimension between CB is 9 meters. So we are having the height as 9 by 15. So since this is again 5 meter, we are having this height as 4 by 15. So positive shear force value would be again area of trapezium, which will be half into 9 by 15, that is sum of parallel sides plus 4 by 15 into base, that is 5 meters into 40. So these values will provide us with the values for different shear forces, that is negative and positive. Negative shear force we are getting as 46.67 kilonewton and positive shear force we are getting as 86.67 kilonewton. Right? Now we have been asked to find out the bending moment at the section. First we will draw the bending moment diagram, that is ILD for bending moment at section C, which will be a triangle of ordinate 6 into 9 upon 15, that is 54 by 15 in the positive sense. Now where to place the part of UDL to get the maximum bending moment? Right? We have to calculate the maximum bending moment, which will obviously be positive. Therefore, we are only calculating one bending moment. Now it is a rule that in the what ratio the section divides the beam. Section is dividing the beam into AC ratio CB, which is basically 6:9, that is 2:3, right? So the UDL will be placed as this. So we will take UDL as something portion here and some portion here. We will consider 2x plus 3x equal to 5. Now by chance we are having it as 5 meters. So we are having x as 1. Therefore this portion will be 2 meters and this portion will be 3 meters. So we are having two trapezium areas to be calculated. So first of all, half into sum of parallel sides. Now for the parallel sides, what we have to do? As the dimension for 6 meter, we are having ordinate as 54. So for 4, we will have the dimension as 36 by 15. Okay. Here for 9 meter, we are having 54 ordinate. So for 6 meter, we will have 36 by 15. We are having two trapeziums. Now we will go with the formula of half into sum of parallel sides. First trapezium 36 by 15 plus 54 by 15 into base into UDL value plus half into 54 by 15, that is sum of parallel sides, plus 36 by 15 into base, that is 3 meter into 40, and we have the whole value as 600 kilonewton meters. So this is our problem that we had to solve, right? Now we are required to find out the absolute maximum shear force for the given chain of loads, that is 20 kilonewton, 60 kilonewton, 80 kilonewton, 40 kilonewton in the simply supported beam AB of span 16 meter. Now what does this absolute maximum shear force means? First we will plot the ILD for absolute maximum shear force in the positive sense, which we will get from plotting the ILD for basically RA and nothing else with unit dimension ordinate, right? Now we will assume that 20 kilonewton load is here, because all the loads, if they are coming on the beam, then only we will get the maximum shear force value. Now another load is 60 kilonewton, which is at distance 3 meter from here. Then another load is of 80 kilonewton and the last load is of 40 kilonewton. Now as we are having distance AB of 16 meter, we are having this height as 1, that is 16 by 16. So we will have the height for 60 kilonewton load as 13 by 16, right? Then for 80 kilonewton load we will have 11 by 16, and 40 kilonewton load we will have the height as 9 by 16. From here we will get the positive shear force. Positive shear force. This value would be 20 into its ordinate 1 plus 60 into its ordinate, that is 13 by 16, plus 80 into its ordinate 11 by 16, plus 40 into its ordinate 9 by 16, and we will get the value as 146.25 kilonewton. This is the positive shear force. Now for getting the absolute maximum negative shear force. Likewise, when we plotted the ILD for shear force in between the section of simply supported beam, we negated the part of RB. Here also we will negate RB as a whole to get the absolute maximum negative shear force ILD. We will have ordinate of unit dimension at B, and we will have 40 kilonewton load at this point. Then at this point we will have the load 80 kilonewton. Then at this point we will have the load 60 kilonewton, and here we will have the load 20 kilonewton. Now the values for negative shear force will be as such. As we are having the ordinate of 1 at B, when the distance of B from A was 16 meter, that is 16 by 16. So to calculate the ordinate for 80 kilonewton load, it will be 14 by 16. For 60 it will come out to be 12 by 16. For 20 it will come out to be 9 by 16. And likewise we will calculate the negative shear force 20 load into its ordinate, that is 9 by 16, plus 60 into its ordinate 12 by 16, plus 80 into its ordinate 14 by 16, plus 40 into its ordinate 1, and we will get the value 166.25 kilonewton as our negative shear force. Right? Now we have been asked to find out the absolute maximum bending moment. Now to find the absolute maximum bending moment, we are not having any section. So we have to put the chain of loads anywhere on the beam to get the absolute maximum value for bending moment. So first of all, we will find out the centroid of the chain of loads. To find out the centroid, let us consider this as the chain 20, then this is 60, then this is 80, and last load is 40. Dimensions are 3, 2 and 2. We will calculate the centroid from the load 20 kilonewton. To find out, we will be required to calculate like 60 into 3 plus 80 into 5 plus 40 into 7, whole divided by all the total of loads, that is 20, 60, 80 and 40, which will come out to be 200. We are having the centroid 4.3 meter from 20 kilonewton load. Right? Now to find out the absolute maximum bending moment, where it will lie. Now if no load is specified, maximum bending moment will generally lie at the center of the span, that is center of beam AB. Right? Now this is the centroid of chain of loads or basically train of loads. Now 4.3 lies nearer to the 80 kilonewton load. Okay, nearest load is the 80 kilonewton load. At what distance 80 kilonewton load lies from its centroid is 5 minus 4.3, that is 0.7 meter. Now to find out that point where we will get the absolute maximum bending moment, we have the center of span as 8 meter and this is the load where it should be placed. So we want half of 0.7 to calculate the most accurate position. Okay, so we will get the highest point at 8.35 from end A, and this dimension will come out to be 7.65 meter. At this point we will get the maximum height. So the maximum load that is nearest to the center of chain of loads is the 80 kilonewton load. Here 80 will come, then here we will get 40, here we will get 60, and the last load we are having is 20. Now the dimension at this height we will have 8.35 into 7.65 whole upon 16. So this height will come out to be 3.99. Likewise, we will calculate all other heights. We will get this height as 2.94, this height as 3.03, this height as 1.6. And now we will calculate the final bending moment value. absolute maximum bending moment, which will come out to be 20 into its ordinate 1.6 plus 60 into its ordinate 3.03 plus 80 into its ordinate 3.99 plus 40 into its ordinate 2.94, and we will have the final result as 650.6 kilonewton meter. Now I'll let you know that how did I get these ordinates. I'll take only one case. I will take the load 40 kilonewton. Now when my base was 7.65 meter, my height was 3.99 meter. So to calculate the height for base 7.65 minus 2 meter, what will be the base? It will come out to be nothing else but 5.65 into 3.99 upon 7.65, and so the answer would be 2.94, and so we will solve these two heights also, right? I hope I have covered each and everything in the ILDs for beams, all the cases and all the numerical parts. Thank you. Now we come across to plotting the ILDs for 3 hinged arches. Now basically a 3 hinged arch is having 3 hinges. First of all, this, basically 3 hinges are provided. One is at A, hinged end, B, roller, and C, it is provided as an internal hinge. The span of the arch is as follows: L by 2 and L by 2. Then we are having a section at point D, which is Z distance from A. Then the height of the internal hinge is small h. The height of the point D is YD. And now, while plotting the ILDs, basically what we do is we assume that a unit load is traveling over the arch. In the last videos, we have seen plotting the ILDs, and I haven't used unit load. I've directly given you the concept for that. But in this, we have to use the unit load. We are having a unit load at a distance x from the hinged end. Now these are the reactions VA, VB vertical, and we also have horizontal reactions in the hinges, right? Now in the concept for plotting the ILDs, we have to plot the ILDs for H, that is the horizontal forces. Then we are required to plot ILD for bending moment at point D, then normal thrust at point D, and finally radial shear at point D, right? This is the horizontal force. This is the bending moment as we have seen in the beam part also. This is the normal thrust, and this is the radial shear, right? Now to start from the horizontal force, first we have to consider ACB as a beam, and in that part what we are supposed to do is VA plus VB equal to 1, because there is only one vertical force to balance this, right? Now we will take moment about point A. So moment of the unit force 1 into x, it is in clockwise direction. Then moment of VB is in the anti-clockwise, therefore we are negating it. VB distance L in the anti-clockwise direction equal to 0, because this is a hinge and hinge doesn't have any moments. So from here we have Vb equal to x by L, and Va we get as L minus x by L, right? Now for finding the force H, we will take moment about the internal hinge C. When we are taking moment about internal hinge C, we consider either AC part or CB part, not both the parts together. So now we take moment about C. As we are considered clockwise moments as positive, so we have VA into L by 2, that is clockwise, therefore positive. Then we have H is in anti-clockwise direction, therefore negative. H into small h, that is the height in the anti-clockwise direction, minus 1 unit force into the distance is L by 2 minus x, also in the anti-clockwise direction, equal to 0 because this is an internal hinge and it doesn't carry any moment, right? Now from here we are having value of VA L minus x by L, L by 2 minus h into h, minus L by 2 minus plus x equal to 0. We will open this bracket and we are having now L by 2 minus x by 2 minus h minus L by 2 and plus x equal to 0. From here L by 2 and minus L by 2 get cancelled, and now we are left with minus plus x by 2 minus h equal to 0. From here we have h is equal to x upon 2h. Now when x is equal to 0 in the portion AC, h is 0. When x becomes L by 2, we have h as L by 4h. Now when we go in this part, that is the CB portion, that means x equal to L in the CB portion, again h is equal to 0 because this equation won't be valid. We have to try solving moment at C by taking CB portion. So from CB portion we will get h equal to 0 again when x is equal to L, right? So now we are having h equal to L by 4 into h. Now for plotting the figure for ILD of h, ILD for h, when x was 0, h was 0, when x was L, h was 0. Only it was highest when x was equal to L by 2. So we have a triangle with the highest ordinate as L by 4h in the positive sense. This gives us the ILD for h. Fine. Now we are supposed to find or plot the ILD for bending moment, okay, bending moment at point D. Again we will draw the arch A, B, C, and this is the point we are having D. We have to find the bending moment at this point, same dimensions as we had taken earlier. Now for bending moment at point D, we consider again the same portion AC. There is a unit load that is at x distance from end A. Bending moment at D in the AC portion, right? Clockwise again we will take positive. So VA into Z, right? It is again clockwise. Also there was H force, this height is YD. Minus H into YD, this is anti-clockwise, minus 1 into Z minus X, again anti-clockwise. We have to find, this is the bending moment for D. We will rearrange the terms. VAZ minus Z minus X. I'll bring this term over here, minus H into YD. Now this portion gives me the bending moment at D when I am considering AB as a simply supported beam. So this gives us beam moment minus H into YD, right? This means we have to plot two ILDs for this thing. So for plotting the beam moment ILD, what we are supposed to do? Beam moment ILD, we will reopen this term. Over here, VA, we had got the value of VA as L minus X into L into Z minus Z minus X. We will reopen the term. So we are getting Z minus XZ by L minus Z plus X. Z gets cancelled and we are left with X into L minus Z by L. Okay. I think I am very much clear up to this point. After this thing, we are supposed to make some calculations. Now since we are supposed to find out the beam moment at point D, so X will become X equal to Z. So we are having beam moment value as Z into L minus Z upon L. Okay, this portion is the beam moment. So we will draw this figure. This is the point D and this is our triangle. Z L minus Z by L. Now in this portion, minus HYD. This is positive and we had seen in the previous figure for ILD for H, it was also positive. But we have to negate H. So what we will do, we will plot it over here only. So this is nothing but H into YD and this is negated portion. So the portion which is not being getting overlapped, it is the final ILD for bending moment, that is this portion. So this is the hashed portion is nothing else but bending moment at D. Right? This is the ILD for bending moment at D in the 3 hinged arch. Now we have been asked to draw ILD for normal thrust. Now from the previous figure itself, that is this figure, over here D point we have to take. Okay, I am only drawing D point over here. I am not mentioning other points. This is the D point, here it is the internal hinge. Now for D point, this is the horizontal force acting, this is the vertical force acting. This will be the normal thrust. This angle I am considering as theta and this force will be the radial shear. Okay. I think the figure is very much clear to you. Suppose this is the D point, this is H, this is V, this is the normal thrust, this angle is theta and here it is radial shear at point D. Now for calculating ND, normal thrust. Normal thrust happens to be V sin theta plus H cos theta. Okay, and for radial shear at the same point QD, we are having V cos theta minus H sin theta, right? Now for plotting the figure V sin theta and H cos theta. V is nothing else but shear forces or the reactions. So for shear force at point D, as we had seen in the beam cases, simply supported beam part, this will be the figure for ILD of shear force. This is Z by L and this is L minus Z by L. This is positive and this is negative. Multiplied by sin theta. Here also multiplied by sin theta. This is V sin theta portion. Okay. And other portion is H cos theta, which is positive over here. Positive, and this portion is H cos. Now, when we have to overlap these two figures, okay, we required some addition. So, the final figure would be, I am making it little bigger. This is H cos theta. Okay. Now, I will reverse this figure for the shear force so that I can subtract this portion. Just creating a mirror image, nothing else. Now, this is L minus Z by L sin theta, and this height is nothing else but Z by L sin theta. This portion is negative, this is positive, and this is also positive. So, the resultant for the normal thrust at point D is this figure. Now, similarly, for plotting the ILD for radial shear at point D, what I am supposed to do is, first of all, I will plot it for V cos theta. It will be same as V sin theta, only we have to add the term cos theta instead of sin theta. Here it will be L minus Z by L cos theta, it is positive, and here it is Z by L cos theta, it is negative. And for H sin theta, this figure, which is negative because we are having a negative sign. Simply we will add these two figures. Okay. So now this is H sin theta, making it little bigger. H sin theta, negative portion, and plotting this. This is positive, this is negative, and this portion is positive. This is Z by L cos theta, and this height is L minus Z by L cos theta. So, this portion, this is the resultant of ILD for QD. Now, let us see. This was the ILD for H. Now, ILD for bending moment at point D. The height was Z into L minus Z by L. Here the height is H into Y multiplied by D. Let's hatch the portion. Everything is positive over here. Okay, this is negative. The whole portion was positive. Now, the final figure for ILD for normal thrust at point D. This was the portion which was positive for H cos theta, right? And we will draw it for the V sin theta portion. This will come out to be like this. This dimension is Z by L sin theta. This particular height, this is negative, this portion is positive, and this height is L minus Z by L sin theta. We will hatch the portion. Okay. Now, finally, we have to draw ILD for radial shear at point D. It is nothing else, but first we will draw it for H sin theta, which stands out to be negative over here. We will take the figure. This portion is Z by L cos theta. This particular height is L minus Z by L cos theta. This is part is positive, this part is negative. So the hatched portion over here gives us the ILD for radial shear at point D. Right? This was the hinge. We were required to find the ILDs for these 4 cases, and these are the final values for ILDs. Thank you.